Welcome to another video looking at expanded solutions to our grade 11 chemistry review. In this video, I'm going to be covering acid-base neutralization problems. So this will cover problems 14 and 15 from the review. Specifically, I'm going to go through the neutralization equation. So let's look at this problem here. I'm given a volume and a concentration of the acid, and I'm telling you that it's neutralizing a sample of a base, and I'm trying to find out the volume of that base. Now, because this is a chemical reaction, you can solve this problem using regular stoichiometry methods. However, because acid-base neutralization problems come up so often, there is a shortcut which allows you to do an equation rather than doing all the steps in stoichiometry. The equation rests upon this principle, which is true at the equivalence point. If you don't remember what the equivalence point is, that's the point at which neutralization has occurred, precisely when the moles of hydrogen ions is equivalent to the moles of hydroxide ions. Where I'm going to start off here is finding the moles of the acid. We know through the molarity equation that the moles of the acid is equal to the concentration of the acid multiplied by its volume. The same thing is true for the moles of the base. The moles of the base is equal to its concentration multiplied by its volume. However, it is not the moles of acid and base which are equal at the equivalence point. It is the moles of the active chemicals, the hydrogen ions and the hydroxide ions, which are equivalent. So we must take that into account. And so the moles of hydrogen ions is going to be equal to the number of hydrogen ions in the formula of the acid multiplied by the concentration of the acid multiplied by its volume. And the same thing is going to be true with the base. The moles of hydroxide ions is going to be equal to the number of hydroxide ions per mole of the base multiplied by the base concentration multiplied by the volume of the base. By definition, at the equivalence point, or if the acid has neutralized the base, the left side of those two equations are equal, and it follows that the right sides are equal as well. So this equation here is referred to as the neutralization equation. It only can be applied and only holds true at the point of equivalence, or when an acid has neutralized a base. At that point there, the left side here is going to be equal to the right side. Let's now take a look at this and apply it to the question at hand. Let's start off in looking at how we recognize this type of problem. We recognize an acid given a concentration and a volume. It talks about neutralizing a base given a concentration. Those are clues that we're going to use the neutralization equation. So let's start off here with the acid. The volume of the acid given is 100 milliliters. The concentration of the acid is 1.5 moles per liter. And in this acid, HCl, which is monoprotic, there is one hydrogen ion per molecule of the acid. For the base, the volume is what I'm trying to determine. The concentration is given as 1.4 moles per liter. And this is a dibasic base, which means that in every one calcium hydroxide, there are 2 hydroxide ions. So for every 1 mole of calcium hydroxide which dissolves, it's going to release 2 hydroxide ions. Now let's substitute these into the equation. I've taken my neutralization equation, rearranged it to solve for my unknown, and substituted in my values with units. Just like with the dilution equation, the specific units do not matter as long as the units match for the acid and the base. So for example, my concentration for the acid and base are both expressed in moles per liter. The volume of the acid is expressed in milliliters, so the volume of the base is going to be in milliliters as well, which we can see by doing some unit analysis and canceling the moles per liter. So our final answer is 53.57 milliliters of calcium hydroxide will be required in this neutralization. Always good to look at your final answer and think about whether it makes sense. We had 2 solutions which were pretty much the same concentration. However, we needed about half as the volume of the base than the acid to reach the equivalence point. And that makes sense because our base here is releasing twice the number of hydroxide ions as the acid is releasing hydrogen ions. Once again, you can solve these problems using the regular stoichiometry methods. And sometimes it's actually an interesting exercise to solve the same problem in both ways so that you can see that this equation here is doing all of the same operations as you are doing in solving something through stoichiometry, just summarized into one equation. The 1 to 2, there's a mole ratio. The concentration times volume there, that's finding moles. Dividing by concentration, that's finding volume again. So the 3 or 4 operations that you usually do in stoichiometry all summarized in a nice tidy equation.